I'm one of Dan's PhD students, currently in my third year, and I've been working mostly on security aspects of machine learning, another relatively overhyped, or maybe hyped at least, technology right now. And today I'm going to talk about some weird, maybe, or sort of interesting connections between adversarial machine learning and ad blocking. So we'll talk a little bit about what the future of ad blocking might look like. So today, the way ad blockers online work, and I guess a lot of people here probably use one, is that they'll try to distinguish, say, organic content like this post on Facebook from Stanford University that I follow, so I don't consider this an ad, from an actual ad I got served from IKEA. And the way current ad blockers do this is by just sort of looking at the markup of the page or sort of comparing the URLs where the content is being served from. Of course, on Facebook, this isn't quite as easy to do because everything comes from the same page. And so this is actually this problem that these kind of techniques on websites like Facebook, and even sort of more generally with ads served by, say, a big provider like AdSense, this might become harder and harder. So there's really this arms race going on where the ad providers just sort of constantly switch up the markup and the URLs. And so these sort of simple ad blocking techniques always are sort of playing catch up and trying to figure out what ads currently look like. And so one interesting idea to consider here is that we as humans are capable of distinguishing ads from non-ads with relatively high accuracy. In this case, for instance, we don't have to start looking at the markup of this ad or trying to think about which URL it is being served from to say, well, this is an ad from IKEA. And one way this is actually being made easier for us as humans is through certain legal requirements, so say from the FTC here in the US, and also some kind of industry self-regulation on ad disclosure. So if you look at this post here on Facebook from IKEA, it actually has a little sponsored keyword in there, and if you've surfed online without an ad blocker, you might have seen a bunch of ads with this little blue triangle, which is the sort of main logo used by the Ad Choices Consortium to indicate targeted ads. And this led, a couple of years ago, some researchers at Princeton to propose this idea of what they call a perceptual ad blocker. And they really did a great work with this in that they actually went out and implemented a real ad blocker, which they call Perceptual Highlighter, which you can download on the Chrome Web Store. It has something like 10,000, I think 13,000 downloads. It still works very well today on Facebook.com, actually. And the way this ad blocker works, the idea there is to try and detect these ad disclosures. And in many cases, this detection happens visually. So for this, they sort of parse the website and use traditional techniques from computer vision to detect these ad disclosures, and this way use the sort of same reasoning as humans would to detect ads. And very recently, AdBlock Plus, who are the makers of one of the most popular ad blockers out there, they sort of went for an even more ambitious approach in that they prototyped a system that relies on neural networks to detect ads directly from a screenshot of a page. So this is really, in some sense, trying to emulate the way a human would go about detecting ads just by relying on the visual content of the page, whereas this ad highlighter plugin, it still relies on some sort of markup information. And this was sort of hailed as the end of the arms race in around ad blocking, that these kind of ad blockers were going to be deployed, that they were going to be impossible to defeat, because essentially the only way you could circumvent such an ad blocker would be to actually change the way ads look or to change these ad disclosures, and this is something that, for instance, for legal reasons is hard to do. And so this is sort of the question that started us on this work, was to sort of understand how secure these perceptual ad blockers are. So of course, we love ad blockers. We also, I think, all of the people involved in this project probably use one of them. And yet we were still interested in sort of figuring out how easy these things would be to attack, just sort of to understand whether these new technologies were actually going to be useful. And as we'll see, it will also be to understand some of the potential new threats that these kind of ad blockers could introduce. So here, it's been running now for a little while, you can see one of these ad blockers that we developed in action. It actually works pretty well. It's running here on I think this is the New York Times, or maybe the Washington Post, I don't remember, but it's basically just detecting ads on this page as the user scrolls through. And this is now the same page, but where we've applied a simple attack where the publisher basically changes the visuals of the page very, very slightly. You won't be able to tell the difference. But unfortunately, the ad blocker is completely fooled and it can't detect anything anymore. The same kind of attacks could also apply to these sort of simpler computer vision techniques that are used in this ad highlighter plugin. So here you have two examples of this ad choices logo. One of them, if you run it through an OCR system, it'll detect this as saying ad choices. The other one on the right, it would just recognize as gibberish. Although again, to the human eye, it seems sort of that these are exactly the same. And then finally, as I said, one of the weird things that could happen here is that we sort of introduce new threats by relying on machine learning to do ad blocking. So this is sort of a demo of an attack that we produce. So here you have a Facebook page with Tom and Jerry. And what Jerry will do is he'll upload some maliciously crafted content that triggers an ad blocker into blocking Tom's content instead. And these are the kind of things that you wouldn't expect to be possible with current ad blockers, and yet once you start using sort of state-of-the-art machine learning tools, some of this becomes possible, and I'll go over the details later in the talk of how this attack works. So this will be the outline for the rest of this talk. First, I'll give you a little bit of insight into how these perceptual ad blockers work, and then we'll go into detail of how we attack them, and finally discuss a little bit about why defending against these attacks is really hard. So at a high level, we sort of view perceptual ad blockers as a sort of generic data classification pipeline, in that to create such an ad blocker, you'd first collect a bunch of web data that you would use to train some kind of classifier, and here this classifier could really range from a very simple, say, optical character recognition technique to a full-blown neural network that you train on screenshots. And here we sort of distinguish these ad blockers by the sort of level of granularity at which they try to classify content in a page, where we call element-based ad blockers basically ad blockers that look at every single element in your HTML page and try to, say, distinguish ad disclosures from non-ad disclosures. And at the other end of the spectrum, you have what we call a page-based ad blocker, which is what AdBlock Plus is trying to do, which is to train a neural network that just takes as input full screenshots of a page. We also introduce a sort of intermediate category called frame-based ad blockers, which I won't talk about here. So when this ad blocker is run on a page, you would first, in the case of an element-based ad blocker, you would have to sort of parse your page into smaller elements. For a page-based ad blocker, you wouldn't do this. And then you would apply some classification tool, which again could sort of range from very simple template matching to full-blown neural networks, and then finally take some actions to block the ads in the page. So here's a little video of one of these ad blockers that we trained ourselves in action. So the reason we did this is that this prototype by AdBlock Plus is currently not public. So we just sort of took the same approach they did. We didn't do this on Facebook. We just did this on arbitrary websites because it was much easier to collect data this way. So what we did is we collected annotated web pages with ads from a whole bunch of news websites from all the nations in the G20 group, and then trained a sort of state-of-the-art neural network to detect ads in these pages. And here we have an evaluation where we run this network on websites that were not ever used during the training process. And you can see that it actually generalizes fairly well. It's not clear that this would be production ready and that it still fails from time to time, but it sort of really shows that there are some distinguishing elements out there that neural networks can use to detect ads. Here you just saw a little mistake where it flagged the weather widget as an ad, but overall it works fairly well in a non-adversarial scenario. So let's now move on to attacking these systems. And the sort of one takeaway I would like you to leave with today is this sort of maybe weird phenomenon, but actually in crypto we sort of expect things to be this way, is that something that works very well in the average case, which machine learning definitely does, usually there's really no guarantee that this will work well once an adversary is involved. And you might have seen about a year ago this really ambitious and sort of optimistic quote by Andrew Ng here at Stanford. It's sort of claiming that nearly anything that a normal person can today do in less than a second, we can automate with AI. And the one caveat I'd add to this statement is, again, that this holds as long as there is no adversary in the system. And so in particular, distinguishing ads from non-ads, this is something that as a human person you would do in probably less than a second. You just take a glance and say, oh, this one's an ad, this one is not. And as we saw, neural networks can do this relatively well too. But unfortunately, now when we're going to move towards attacking these systems, we'll see that it's actually very, very easy. And the reason is this very curious phenomenon called adversarial examples. And these were introduced in two seminal papers by Szegedy and his co-authors, and then Goodfellow and his co-authors. They're actually both of the papers basically written by the same people about 4 or 5 years ago. And what they discovered is that the neural networks that we're now training for, say, image recognition, they work fairly well, and that if you give them this image of a panda on the left, this neural network, this was the one that was, I think, used in Google's image classification system at the time, would tell you with relatively high confidence that this is indeed a panda. What you can then do is craft some very specific noise that you see here in the middle, just blown up so that it's actually visible. Here, the scale of this noise is roughly 2 pixel values. So every element in this noise is between sort of plus and minus 2 over 255. And when you add this noise to this image of a panda, you get this image on the right, which to us looks completely indistinguishable. And yet the model is now certain that this is a gibbon, which is a small monkey. And you could change this noise to make the model basically believe whatever you want. You could make the model believe that this is an image of an airplane, of a fridge, of a robot, whatever it is, basically what it has learned to classify things as. And creating these adversarial examples is actually strikingly easy, in that you basically do the exact same thing. You use the exact same techniques as people used to train these models in the first place. So at a very high level, when you try to train a neural network, what you do is you take the millions of parameters that make up the model and just sort of tweak them using gradient descent in such a way that the output of the model becomes closer to the class panda. And now when you try to create this noise, you basically just reverse this optimization problem on its head and say, well, now we're going to try to tweak the input pixels, of which there's maybe a few 100,000 of, such that the output of the model gets closer and closer to the class gibbon. And these adversarial examples, they're really a pervasive phenomenon that has now been studied. There's thousands of papers on the topic in the last few years. And there's already been a bunch of proposals or sort of papers written about the security impacts of these attacks. So the first example is a paper from a few years ago by people at CMU, where they constructed these sort of 3D printed glasses that would fool a visual recognition system that here takes a photo of Lucho Bauer and recognizes him as, well, as Mila Kunis instead. No, this is not Mila Kunis, sorry. I forgot the name of the actress. It's another famous actress. And there's been other examples of these sort of physical attacks here. These were printed adversarial examples that even after you scan them with a camera and feed them into your network, they're still misclassified. There was this really cool paper by students at MIT that 3D printed this turtle that gets recognized as a rifle. There were other papers, one in which I was involved, that did this with stop signs that were misclassified by the type of visual system you would expect some self-driving cars to maybe use. And also in other domains than images, there's been, for instance, some work on trying to fool audio models that say the type of thing you would have in your Alexa or in your Google speech-to-text engine. And in all these, the principle is basically the same. You start with one input and tweak it a tiny bit in a way that a human wouldn't be able to tell the difference, and all of a sudden everything fails. And unfortunately, and I'll get to this a little bit more in the end of this talk, the landscape of meaningful defenses currently looks a little bit like this, in that especially when the adversary has sort of direct access to the model that he's attacking, and we'll see that in the ad blocking case this is really true, we really have no idea how to get rid of these types of attacks. We don't know how to train models that behave in a robust way once an adversary is involved. So let's now look at what this means for perceptual ad blockers. And first I'll talk about this type of page-based ad blocker, like this Sentinel project of AdBlock Plus. So again, this is an ad blocker that gets fed in a full screenshot of a web page and tries to detect where the ads are in this page. So the first attack we'll look at is sort of the most canonical attack you might think of for an ad blocker, which is to take an ad and try to make it unrecognizable by the ad blocker so that it still gets shown to the user. And the adversary we'll consider here is the website publisher, say the New York Times. And so the goal of this adversary will be to tweak the website in a way that the ad blocker just stops working correctly. You could also consider other adversaries, say the ad network could try to tweak the ads that it serves to make them unrecognizable. We have attacks of this kind in our paper as well, but I won't discuss them here. So this is one attack we looked at. So if I'll go into the details just in a second. First, if you remember this picture of the panda, there what happened is that as an adversary, you were basically taking every pixel of the input image and tweaking it a tiny bit so the model would misclassify things. Here in the web context, things are a little bit harder in that the input to the ad blocker in this case is a screenshot of a website. But the adversary, say the New York Times or any other publisher, they sort of have to push an actual HTML page out there, so they don't have really access to the pixel level representation of this web page directly. It turns out that actually you can do an attack that's fairly similar to the one we saw for the panda just by abusing some CSS properties. So what we did here is we created a tiny patch of noise that you see there on the right. And just by using some simple overlay tricks, we can get this noise to basically be replicated over the entire page. And then again, we make this noise very, very small in magnitude so that if you look at the page, you wouldn't recognize even that this layer of noise is there. You can still click on elements, so you really don't notice that anything on the website has changed. But you see that the ads are now no longer blocked. So the model, it does take this noise as input when it takes a screenshot of the web page, and it gets completely fooled and has no idea anymore where the ads are. And we tested this type of attack on sort of 20 web pages that we never used when actually creating this patch. So this attack is what we call universal, in that it sort of generalizes to all types of websites on which it gets applied. And so this means that this type of attack would be very easy for a publisher to deploy at scale, in that once this attack has been created, every single publisher out there could just use it and fool an ad blocker. And we also have other techniques in our paper that I won't get into too much detail here to make this attack sort of more stealthy by not having to rely on any of these crazy CSS tricks, which also, again, makes it harder for the ad blocker to then remove the attack or sort of detect that it's happening. The other type of attack we'll look at is sort of an orthogonal goal you could consider to get rid of ad blockers, which is just to detect them. And when you surf the web today with an ad blocker, you notice that a lot of web pages do this, right? They detect an ad blocker and then they just remove, just tell you to disable it. And here again, we'll look at this from the website publisher's perspective. And here we just had a very simple attack where the publisher actually just perturbs a tiny bit of the banner on, say, this BBC Sport page. And now all of a sudden the ad blocker detects an ad where none exists. And if it were to block this part of the page, you could presumably detect this and tell the user to disable his ad blocker. And finally, I'll get to this new threat we call privilege abuse. This is the example I showed earlier, where one user could upload content that gets the ad blocker to suddenly block another user's content to which the first user should have had no access. And the reason this works is that these type of neural networks that we use here, they sort of generate predictions just by taking the full input, the full page information into account. And this kind of means that the way this model will segment the page need not be aligned with sort of the type of web security boundaries you would expect. And so any perturbation anywhere on the page could actually affect the model's predictions anywhere else. And this is, of course, a problem that can arise when using these neural networks in a web setting. So in terms of the defense, why this is hard is just because the threat model here is basically the worst possible you can imagine, in that the adversary here, he will have white box access to the ad blocker. He will know how this ad blocker works, what kind of model it's using, because he can just go and download it itself. And we saw that you sort of, as an adversary, you can exploit both false negatives and false positives in the classification to either evade ad blocking or at least detect it. The adversary also has sort of time to prepare these attacks online, and the ad blocker then has to defend in real time in a user's browser against them. And then, of course, if you were to do the data collection in a crowdsourced way, there's even more avenues for attack that I won't go into detail here. In terms of defense strategies, I'll go over these really quickly because they don't work. So one thing you could imagine is that the ad blocker would obfuscate the model in some way. This is still easy to attack, even if you assume that the classifier is a fully black box algorithm. We have attacks that work in this setting. If you apply randomization to the classification in any way, we have ways to make the attacks robust to that. This doesn't work either. Another thing you could do is try to anticipate or at least detect attacks and try to train your model proactively against the types of attacks you notice in practice. This is called adversarial training. This was actually proposed in the very first paper on adversarial examples. And this sort of creates a new arms race where as soon as you've trained your model to resist one type of attack, the adversary will just switch to a new one. And this is a really big open research problem on how to sort of scale this type of adversarial training to really create models that are robust. And so far, from what we've seen, the adversary just always wins. And then finally, one thing you could consider is to simplify the problem. So instead of trying to run your neural network over a full page, you could consider these sort of simpler techniques like this plugin we saw at the very beginning of the talk from the people at Princeton that, say, just tries to detect a very simple logo like this ad choices disclosure icon. And for this, you can use much simpler and sort of lightweight computer vision techniques. And you can't sort of just try to detect these logos just by doing sort of equality testing on images, because there's actually a lot of different logos that people use in practice. Here are just a few that I found online by surfing through a bunch of web pages that use this disclosure. So you need a technique that's sort of robust to these kind of changes anyways. And unfortunately, it turns out that even for these simpler techniques like OCR or what's called perceptual hashing and other techniques, you can still create adversarial examples. It turns out that all the logos that I've shown you so far are adversarial examples. This is what the original ones look like. So these, if you fed into these computer vision algorithms, they would detect them reliably, but the ones at the top, they would have no idea what to do with. There's also a false positive here on the slide. You might not be able to see it, but this thing, if you feed it into SIFT, I won't tell you exactly what this algorithm does. It's just sort of an algorithm that tries to compare images. It will actually tell you that this thing here is very, very similar to an Ad Choices logo. And so this doesn't really solve the problem either. So in conclusion, in a sense, emulating human detection of ads, it could really be the end game for ad blockers, in that if we could do this reliably, well, it's true that there don't seem to be that many avenues for attack anymore if we need ads to be distinguishable by humans. It just turns out that doing this with current computer vision techniques is extremely hard because we have no idea how to resist these adversarial examples. And the other big problem here is that these perceptual ad blockers have to survive a very strong threat model where the adversary basically just has access to the model in an offline phase and can prepare attacks however he wants to both evade and detect ad blocking. In our paper, we also show that you can apply similar attacks outside the web. So we found this project. This is a startup in France that tries to do ad blocking for radio podcasts by just feeding the audio stream into a neural network classifier. This also actually works very well. So if there's no adversary in the system, their algorithm sort of detects which parts of the stream are ads and then just sort of cuts them out. It turns out that there as well, you can just tweak the audio signal a tiny, tiny bit in a way that to our ears is indistinguishable, and all of a sudden the ad blocker thinks that the ads are just part of the regular program. And so if you're interested in learning more, we have a paper on this topic that's online. You can find it on archive or on my personal webpage. We also released all the code we used to train these ad blockers and to attack them on GitHub, where we have a bunch of demos. And yeah, that's it for me, and I'm happy to take a question or two, if there's time.
Right, do we have time for questions? You have some questions over there?
Yes.
Because I think, thank you. I think most, like in the turtle example that you show, it was a little bit difficult to really make sure that the adversarial sample would be completely maintained throughout the changes in the camera. So here, similarly, I think that if you chop the web page and take a smaller banners and analyze, not for looking for a particular sign, but rather analyze, then the Tom and Jerry attack would not be possible.
Right. So for specific attacks, it's possible that for some of them you could get rid of some of the attack artifacts. So this also goes back to one point I glossed over a bit quickly, which is sort of randomized defenses. So you could imagine that you would instead of just running your ad blocker on one screenshot of the page, you would take sort of a number of random crops of your web page and then classify each of those. And it turns out you can create attacks that will end up being robust to these types of approaches as well, usually by just making sure your perturbation covers the whole page in a way that's robust to random cropping. For the Tom and Jerry attack specifically, there, of course, if you end up cropping out the part of the page that one user controls, his attack won't work anymore. And there, in some sense, you will need, to make your defense. Make the defense aware of these web security boundaries that you want to be in place. So the takeaway here is really that if you do not do that, if you just let the neural network sort of by itself figure out how it should segment pages, there's a very, very little chance that this will agree with web security boundaries that we want to be in place. And of course, by making this more explicit in your model or in your general algorithm, some of these attacks will be preventable, but not all.
Although you would also make the page more easy to scrape if you do that.
Yes.
So you would introduce other attacks on your page.
Yes, yes.
Do you want to repeat that? Or did you repeat that?
Yes, so Dan was saying that by doing this, you would also make it easier to scrape the page if you ensure that I guess that the ad blocker can sort of access every single chunk of the page independently. It also makes it easier to just extract these portions of the page by an adversary.
Yeah,
yes.
Let's take one more question. Yeah.
Hey Florian, very nice presentation. I'm Rajurshi Gupta from Avast. So I noticed that a big part of the problem that you mentioned is because of this uneven situation where the attacker has pretty much all the marbles and the defender has very few. Do you see a situation whereby we could turn that on its head by having like a cloud-based service which in some way is rendering these kinds of web pages and detecting that, and detecting the presence of an attacker, and then sharing that information with the web browsers that says, look, you are going to a page that is actually using this kind of an adversarial ad blocking technique?
So I guess you could imagine having a sort of ad blocker as a service, which would introduce a whole bunch of other issues, especially from a privacy perspective, I guess, and from a bandwidth consumption perspective. Another issue there is that, as I mentioned earlier, the problem with these neural networks, with defending against these attacks, is that even when you do not give the adversary sort of white box access to the model, if you only, say, give the adversary the ability to query the model and see the responses, that's still enough to mount a very, very successful attack. So you could imagine that in this case, you would have this service running somewhere in the cloud, and an adversary would just sort of send it some web pages to classify and try to disguise this as just natural traffic, but use this to mount a strong attack that it can then deploy. So this makes the work of the adversary a little harder, but not that much. And yeah, for the sort of privacy and bandwidth problems that would come with it, it's maybe unlikely that this would be the preferred solution. Thanks.
Jim had a question.
Microphone on? Okay. Yeah, my understanding or perhaps misunderstanding of adversarial training is that you needed direct access to the classifier. It seems potentially, and I was surprised actually you had a universal evader for the classifier. It seems potentially possible if you take the asymmetry between the cost of training, which is usually large, and the inference time, which is small, you can have an endless stream of classifiers, released on a daily or weekly basis, much faster than an adversary could retrain, and that would seemingly, unless you had this universal adversarial training, which is contradiction with what I misunderstood, I guess.
Yeah, so just a clarification there, the adversarial training is meant as a defense, so this would be the ad blocker who would proactively retrain their model to resist attacks.
Correct, on a daily basis, for instance.
Right, and so this is actually an expensive process. Whereas the attacker's goal or what the attacker has to do to create these type of attacks doesn't take a lot of work compared to training a model.
So you're saying the training is fast. The training for an adversary is actually faster?
Yes, yes.
Great, thanks, Florian.
Thanks a lot. Yeah, I'll leave this here.